Okay, so let's talk about databases, but no discussion of databases would be amiss if we didn't talk about the language we're going to be programming in. And this is going to be our next programming language because this really is a language. It's called SQL. Some people pronounce it SQL. Some people just say SQL. Either is fine for me, right? Tomato, tomato. If we look at what MDN has to say about SQL, it's a descriptive computer language designed for updating, retrieving, and calculating data in table-based databases. Right? And that's primarily what we're going to be doing when we talk about back-end systems, is updating, retrieving, and computing data in order to give that data to our front ends. So you all did the choose your own API example, right? And you connected your React front ends to some API that somebody wrote. Probably most of those APIs are supplied by a database, right? If you did like a random joke one, those jokes probably exist in a database, right? Or if you did something like picks a quote, right? Or is movie reviews, or it's the weather, right? A lot of that data must be stored somewhere on a server or a computer somewhere. Most of the time, that data is in some kind of database. Right? So why do we have databases? Right? When creating programs, understanding and correctly implementing the business logic is important. Right? What we just talked about this morning, right? PDAC and algorithms and whatnot, those things are super important. That's what we get paid to do. But we also have to make sure that we safely and correctly store that data somewhere. Right? If we were talking this morning, right, about accounting software, right? We have ledgers, right? We have to store the transactions somewhere. It's not enough just to be able to compute your balance correctly. We have to make sure that that data is stored somewhere, and that data is secure and it's safe. Right? That's primarily what we're looking to do. So why would we choose databases? Let's talk about ways we might store information. I'm going to shrink this so I can read it. Right? What if we just stored our information in memory? Right? We've done that so far. We've made little arrays, or we've kept things inside of state, inside of our React application. But we know that when we reload the page, that data goes away. Right? If we consider storing information in memory, when our users add data, right, we store them in arrays, objects, dictionaries. They're super simple to think about, and they're easy for us to implement. Right? But if we shut down or restart, we lose all of this. The second half of it's very hard to share that information between users running on different computers. Right? As you're making your little to-do list or color picker, and you want to share that with somebody else, right? We don't have a way of doing that from what's running in your browser to what's running in my browser, right? Because my browser has a memory and your browser has a memory. I think we've played with local storage, right? Let's store some things in local storage so that when we go back to this page, we can reload it. That's great. It's actually kind of like a little database, right? But what's in your local storage can't be shared with my local storage. And this is why having a backend is so important. Cool, so we learned some other things, right? We have JSON files. There's also formats called CSV, comma separated values. And if anybody's ever worked with spreadsheets before, you've probably come across CSV files. They're pretty common, right? Maybe we consider storing that data inside of a local JSON file or any other what we call linear file storage format, right? We mean linear in terms of they're represented by independent lines of text. Right, like our JSON file, right? Line 1, line 2, line 3, right? It's pretty much a natural extension of storing the data in memory, so much so that we have a form for this. We have a name for it. We call it a serialization format, right? Serial in terms of things that come in order, not like breakfast cereal, S-E-R, like a series, like I've been binging a series on TV all weekend, right? Serialization means in an order. By the way, I've been watching The Expanse. Has anybody seen The Expanse? Oh, it's super good. I've been literally binge watching it since I got back from vacation this weekend. The concept of serialization is to take information we've stored in memory and represent it in a series of characters or bytes that can be stored in a file. Right? You open up your JSON file, right, that you made as part of your React app, and then literally you can start on the first character and work your way line by line to the end, right? And every character and line is in some order, right? And it works pretty well. I think you all probably did JSON files for something like Octocats, right? Maybe you made a state and then you put that in a JSON file and you'd require the JSON file to get the data. It's great, but it has some flaws that makes it a poor choice for how we store data, right? These files are really easy to append to, right? You go to the end of the file and you type more data, but they're difficult to delete or modify within, right? It's hard to find the third Octocat in that file and get rid of it or change it, right? What has to happen to your computer is, right, if you think about rewriting that Octocats file, all the first characters are the same, so we could leave those alone. But as soon as we get to the change, we have to rewrite the entire rest of the file. If we remove one character from the middle of that file, what your VS Code actually does is it leaves all of the first lines alone. And from the place you make a change, it rewrites the rest of that file. So imagine if you had 1 billion Octocats in that file and you delete the third one. In a file like that, you're rewriting 999,999,997 Octocats. That's really not efficient. It seems really fast, right, when you're editing these files, but it's not really great for removing or changing things in the middle, right? Because these are streams of information, right? So we often sometimes say these are serialization streams, meaning that information comes at us in a flow of data, and changing something in the middle is hard, right? Even here we say it's acceptable for small applications where rewriting the entire file is slow, right? But for large applications, it doesn't work. For 143 Octocats, resaving that file takes 1/1000th of a second. 1 billion Octocats is a different story, right? The other part is, what if there were multiple users or servers attempting to do that work at the same time? Well, if I was rewriting the Octocats JSON, right, and then Angela wanted to rewrite the file at the same time, she would have to wait for me to be done writing that file before she could write her copy of the file, right? We both can't be changing that file at one time, right? Files are single user in this way, right? So we want the ability to read, update, and delete any information we want at any time without having to rewrite the entire list of data. That's one of the things we need a database to do. And we also know that we want multiple users to be able to get at that data and change it at once, right? That accounting software doesn't really work if I sit down and use the accounting software and nobody else can use it while I'm working, right? If they're locked out of that accounting system until I press save, that's no good, right? So they have to be multiple users. So for databases, we're looking for a couple of things, right? A database allows us to persist and query data we need for applications, and they are a good choice because they have 4 features, right, that we call ACID, A-C-I-D. That's a good way of remembering this. And you may find if you're applying for a backend developer job, someone may say, like, what are the qualities of a database? And if you can say the word ACID, right, you've tripped that keyword. And if you can remember what it stands for, even better. And if you can remember why these things are, even better. And they stand for, the A, C, I, and D is for atomicity, consistency, isolation, and durability. These are the 4 things that we need out of a database. Okay, so what do these mean? Atomicity means the ability for the database to allow multiple changes to be requested at once and have either of them all fail or them all to succeed, right? And it comes from the idea of an atom, right? We used to think of the atom as the smallest bit of the physical universe, right? An indivisible thing, right? For instance, if we were making a banking application and we wanted to withdraw $10 from Andy's account and then add it to Barbara's account, we might first write a statement to decrease Andy's balance by 10, and then a second statement to increase Barbara's balance by 10. If these two statements aren't guaranteed to succeed in pairs, then we have the possibility that we would decrease Andy's balance without correspondingly increase Barbara's. What if our code said, remove $10 from Andy's account, and the next line of code said, put $10 on Barbara, and the lights turned out, right? The power went off to our computer. And we turn the computer back on, well, what's the problem? Andy's account has $10 withdrawn from it, but we never added it to Barbara's. We can't allow the database to become inconsistent. We need that withdrawal and that deposit to be one thing. Either that whole sequence of things works or the whole sequence fails. We talk about consistency. The data we store is consistent. Any rules the database enforces are applied when asking for changes. An example is when creating a user to our system. Notice a few of you have users in your Capstone wireframes, right? We require the user to have an email and a password. If we try and create a user, but the email is blank, we don't allow that data into our database, right? Consistency means any data that's in the database is assumed to be valid because we made sure it was valid when we put it in, or we made sure it was valid when we changed it. Right? So consistency means that it follows the rules of our system. Right? Isolation allows for multiple database requests to be handled concurrently, meaning reading and writing multiple rows at a time, or multiple people asking for data at a time. Right? This is what allows databases to be good for multiple users. Right? This is why our API can be requested from anybody on the internet at any time. We don't care how many people are asking for that data at any time. Right? Isolation. If I'm depositing money into my account, you can be withdrawing money from your account at the same time, and the database isn't going to care about that. It's going to work just fine. Right? Durability ensures that once the data is written to the database does not lose information. Right? In case of the database crashing, the computer crashing, or the system crashing. Right? Once a database says that a row is updated, it's updated. Right? And if we shut the computer down or the power is lost, we should not lose that data. Right? And what we find is different databases have different levels of A, C, I, and D. Right? Different database engines or database products, like if there was a score of 0 to 100, right, they're going to have different scores for each of these, right? No one scores them that way, but we can think of it that way. For instance, there are very good databases that have great atomicity, consistency, isolation, but they're not very durable, right? There's great databases that have fantastic atomicity, consistency, durability, but lack isolation. They're only single user databases, right? In fact, there's a database in your browser that's not an isolated database because you're only one user, one browser working that. Your local storage is an example of that, right? It has all of these things. It has atomicity, consistency, and durability, but it has a 0 score for isolation, right? It's just one browser at a time can update it. Then we can talk about two different kinds of databases that we have. And you'll hear people talk about the SQL versus NoSQL. And really the difference, I like to think of them as table-based versus document-based. Right? There are two overarching types, and you'll hear people say, hey, do you know, you're a back-end developer. Do you do SQL or NoSQL? Really what they're asking is, do you do a relational database or a document database? And what we're going to teach you all is the relational database, because it's the primary thing that we see. But the world is starting to implement more document databases. It really depends on the kind of business problem you're solving and the kind of world you're working in. Right? SQL that we're learning is a table-based paradigm. Right? We store and arrange data in an Excel or spreadsheet-like format that focuses on normalizing our data by looking at relationships and structure. So everything that we talk about in relational databases, we're going to talk about thinking about things in terms of rows and columns. Everything is a two-dimensional array of data, right? Kind of like if you ever worked in Excel or spreadsheets, right? You've got column A, B, C, D, and rows 1, 2, 3, 4, 5. And we talk about cells like row, like we talk about D5, right? That's column D, row 5. Databases are the same thing. We're going to have different tables for all the things that we store. And then we're going to talk about how we relate those two different sets of tables together. This is why we call these relational databases, right? In terms of what we do SQL. And SQL is the language that we talk to the computer in order to get information in and out of those tables. NoSQL is kind of the opposite of that, right? At a high level, NoSQL stores data in a form other than the table structure SQL. It's very loose. So if you find in your business problem that the type of data that you get varies quite often, then a relational database isn't that great, right? We talked about there being columns of the kinds of things that we're storing. Maybe it's for people, right? First name, last name, middle initial, phone number, date of birth, right? Hey, I'm planning a wedding, right? Yay. I have an Excel spreadsheet of all of the people that I'm inviting to the wedding. And it's literally that. Name, relationship, city, state, zip, address. Are they from in town or out of town, right? Very much a table-based thing. If I were storing, I want information about a person, I may not know all the things about a person I'm gonna store, right? There could be lots of different things we store about a person. A document database would allow me to store different things about me than it wouldn't be the next person I'm storing data about, because it does not restrict me based on the columns. That has a lot of huge benefits, but it also has some detractions from that.
And does the document, the NoSQL, allow you to add in tables and stuff as documents do, like insert table, insert pie chart, insert?
Well, you could store a table of information inside of the document. So one of the things in the document that's about Chantel would be, hey, here's a table of information about her.
So you can do both inside NoSQL?
Yes.
And pie charts and stuff like that?
Yes. Well, pie charts are more a visualization of the data.
Okay.
Whereas you may say, hey, get me this data out, and I want you to format it like a pie chart. Right, that's more like the CSS is to the HTML.
Oh, I see.
Yeah. So like pie charts and graphs are visualizations, just like HTML is our structure and CSS is our visualization. Charting of those things is relationship like that. What's hard in document databases is the relationship part is very hard. So you gain flexibility in terms of, I can store any information I want,
Right.
but then making relationships between data becomes difficult. And you have to think about it a different way. So mostly what you're going to see in the work that you do here, and primarily, chances are, 90% of what you all find, in your first jobs as developers are going to be relational databases. So we're going to teach you that. Cool. So let's think about what we want to do now. Yeah, let's cover this, and I think maybe what we'll do is when we get back at 3, we'll actually make some tables and whatnot in our database. So let's talk about the concepts, and then we'll break, and then when we get back at 3, we'll go through creating some tables in the beginning. All right, so SQL databases store and manage data into tables. These tables are made up of rows, right? We can think of Excel, we talked about that. So tables are the container for our data. And what we find is usually a database is made up of multiple tables, one for each thing that we're storing, right? We've come back to our nouns and our verbs. Typically the nouns in the description of our system are going to be our tables. So you all have started making wireframes for your projects. You probably have started to use some nouns in the description of what you're writing on those pages, right? If you were making a system that is a movie review, you might have movies, you might have directors, right? You might have reviews, stars, right? All of those things might end up being tables in our database. So as you start working through wireframes, one of the reasons why I ask you to do that, it starts identifying those major quote unquote things in our system. Most of those will probably become tables in our database. For instance, imagine we're building a system to manage books for a library. We could create a database named book collection, and in that database, there's probably going to be a table called books, right? What are we managing? We're managing books. We should probably expect there to be a table called books. And in this books table, we would design columns that represent the specific data about books we wish to track. Each row in the books table will represent a unique book in our collection. So if we're modeling that, as you go through your wireframes and you're looking at, hey, this page shows all the movies, right? You're going to think about all the information you're showing about a movie are probably going to be columns in that movies table, right? This is why breaking out all of the screens and detailing everything that's on a screen is so important, because that level of design will influence when you sit down to design your database. And that's one of the things we're going to talk about this week is how do we move from, hey, here's our wireframe, how do I know what tables to design? And there's a whole aspect of design just based into databases. Right? Columns are part of the table that define the structure that we often call the schema of a table. Schema, S-C-H-E-M-A. We talk about a table schema. We're talking about the columns that that table has, their names and their types. Right? We define the attributes of the thing. Every column has a data type that defines and restricts what type of data we can place in that column. Right? So unlike Excel, where you can kind of put anything in a column, here we're going to tell the database, no, this column in our table is a title, and it has a particular type. Right? In our books table, we want to store specific details, such as maybe the title, the author, and the genre of the book. Right? Maybe that's what our book list wireframe told us to do. We're going to name these columns title, primary _ author, and genre. In a language like JavaScript, Ruby, or C#, we would normally define each of these as a string, right? Because the title has letters and numbers in it. A primary author has letters and maybe numbers in it. I don't know if you've got a 3 in your name, and a genre. Right? In a database, though, we have some choices for the type. Character, varchar, and text. We'll talk about those again when we go to make some tables. In our case, varchar and text makes the most sense. Right? And there's some links in here to Postgres docs on types. Right? Finally, we're going to store data in rows. Each row represents one thing, in our case, one book. In our example, a row of data would contain The Cat in the Hat as a title, Dr. Seuss as the author, and kids as the genre. Right? The important part here to remember so far is that we have a database. Databases contain multiple tables. Tables contain multiple rows. And each one of those rows has the same columns or attributes for every one of those rows. Right? In our case, we're going to have a library. We're going to call our database book collection. It's going to store information about books. Each book has a title, an author, and a genre. Right? Database, table, columns. What we're going to find with a database engine like Postgres is there are tools that we're going to run to create these databases, give us interactive access to our database, and a language that's going to allow us to create some tables and then modify the data that's inside of them. And we're going to use a language, and it very much is a programming language, like we learned JavaScript to modify variables and modify the DOM. We're going to learn a different language that's going to sound a little bit more like English than the other languages you've seen so far, so yay for that, to allow us to modify our database. Cool? Makes sense? Kind of why we're doing it? Questions? I saw a hand up and then down.
Yeah, I was just wondering about the rows and columns.
Mm-hmm.
So would it be somewhat like rows would be represented as like a category, whereas the columns within that row would be just various data within that?
It would look a little bit more like this. So let's say we didn't have databases. All we had is a spreadsheet. So in a spreadsheet, can I zoom?
On the bottom, you can increase the...
Oh, is this the zoom here? Yeah. If I could, if my mouse was gonna... There we go. Thank you. Right. So maybe we have Cat in the Hat by Dr. Seuss. Kids. Right. 1984 by George Orwell. Science fiction. Right. Right? Maybe we have something like this, right? Each one of these rows here is a different book. Each one of these here is a different attribute of that book. So much so that when we're working in spreadsheets, we often put a column here like title, author, genre, right? So this metaphor of a spreadsheet works pretty closely to the same metaphor as a database, so much so that we might call this books.
Right.
So if you've done any kind of spreadsheet stuff before, you've already done essentially relational databases to a large extent. A lot of what people created out of spreadsheets came from the idea of relational databases. Right? Relational databases actually came first. Spreadsheets came second. But they have a lot of similarities. This is kind of the visual that you're looking for when you think about a database table. Our rows here, rows 2, 3, and 4, are individual books. Our columns, in this case A, B, and C, are the attributes of a book. So a lot of what we do when we are making our databases is thinking about the nouns, books, authors, maybe patrons, right? Maybe genre becomes its own table because maybe you want to store more than just the name of the genre. We'll talk about what happens when we have more than one attribute to something. But you're typically talking about instances of those nouns and the things that describe those nouns. The title of a book, the author of a book, the genre of a book, right? You can think of those things being columns. So if you look back at the wireframes you've done, this is why having descriptions of what these things are and even having some examples of what those screens would look like with fake data helps you start to identify these kinds of things, right? And the more that you start to drill down on your wireframes and start to build those mock-ups of those HTML pages, that will lead you to starting to break things down to get to this level of detail, right? And that's the bridge from the front end to the back end, right? Your front end is going to start saying, what are the things I'm tracking? What are the attributes of those things? How are they related? What we're going to see when we dig into creating databases is we'll figure out how to store and represent that in the back end. Cool. It's 12. Let's take a break. And then you're welcome to read ahead. But the rest of what we're going to talk about today is how we make databases, how we create tables, how we put things into tables, how we bring things out of tables, how we update what's in a table, and how we delete from a table. Okay, so feel free to read ahead. When we get back at 3, we're going to walk through all of this. And I just want to make sure that everybody's Postgres environment is working okay, and we can create databases and tables. So that's what we'll do when we get back together at 3. Cool? Cool.
Thank you.
You got it.